curves. And then talk about global process curves. Remember, if for the plane curve, closed curve on the plane, and the total curvature is going to be 2k pi. Okay, so let's recall the following. Okay. For a closed curve C in R2, this is a notation called total curvature, the sine curvature. This is going to be 2 pi k. K is going to be integer. Okay, so curves could be like that. It's closed. Okay. We did we can come back to this again. How do we prove that? We use a formula for the tangent vector, okay, which is can be completely determined by the integral of the sine curvature. And because it's closed, when it's come back, so you end up with the same value for the tangent vector. Therefore, the angle, okay, we call turning angle, must be 2k pi. Okay. And now we are going to study curves in space. Curves in space in general is very complicated. You have involved two curvatures, right? And one is portion, the other one is curvature. Okay. For a curve in a three-dimensional space, right? Including three-dimensional space, C. And we use a parameterization, right, to get, right? Now, if this is arc length, right? If this is arc length, then you have a tangent vector T and the normal vector N, and cross product of this, right? This two. Okay, you have a friend. Right? So this friend, this friend satisfies the following equations: T equals T dot equals K and N. Okay, and then N part is going to be negative K T plus tau, and B prime is going to be negative tau N. Okay. So you have three quantities. That's two quantities, K and tau. Tau is called a portion, K is called curvature. So those are two independent quantities. Yeah, this is two independent quantities. And even curvature and portion. And one frame at a point, you can uniquely determine a curve going out and completely determined by those two curvature K and tau, such that their frame, this we call the orthogonal frame. Is the given solution T and B. Okay, you solve this system of different equations. You get C of S, N of S, B of S, and satisfy initial condition, right? From ODE you can show that. Then that means you can tau uniquely determine a curve whose curvature is K and portion is tau, and up to some notation translation. Okay. Now let's focus on a curve. Focus on a curve on a sphere. Assuming that C is a curve S1, S2, the unit sphere, right? Yeah, let's look at how special it is. So we can consider it's a space curve, right? But it is on the sphere, right? Right. Now it is on the sphere. So we still use that, right? So gamma S. We assume that the length is going to be 1, right? And there's from alpha to that, right? Into a piece of curve. Right. Let's do some computation. Okay. It's it is a unit sphere, so we also have this identity, right? 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 So this is yeah, it has a unit length. So just go ahead and differentiate. When you differentiate, you will get this, right? Now twice of that. Then this is a capital T, okay, right? That's a TS. So that means tangent vector up to the curve is perpendicular to gamma S. Okay? And therefore, on the other hand, right, TS is perpendicular to NS, and TS is perpendicular to BS, right? So this unit vector, so this implies this unit vector can be written as a linear combination of NS plus BS. Okay, and it's unit vector, so where S square plus BS square equals 1. So it's 1, then you can even express them as sine cosine if you want. Okay, so eventually we can do that, man. All right, so we have this identity, right? So let's differentiate again. When I differentiate, and then you get A prime S and S plus B prime S and BS. But also you have AS, the derivative of NS. What is N? N is going to be negative K TS plus the quotient BS. Okay, what is a B prime? B prime is negative quotient and NS. Okay, so let's simplify it. Group them together. Only one term is TS, so it's negative AS TS. Okay, right? All right, so how about the N? Coefficients of N, right? You have, no, it's not B prime, it's just B, okay? So let's do the count. Yeah, group them together. So I have NS, right? So AS minus BS tau S. So this will be NS. And then how about the B? B prime S plus AS tau S. All right, but if you compare both sides, this is just a TS, right? Because the derivative is a tangent vector. And then T and B are linearly independent. So this implies 1 equals negative AS KS. And then you also have this 2. Wow, we are very familiar with these 2 equations. These 2 equations are very familiar. Once you get this in the study of the sine curvature, right? So that means That means since as squared plus b squared is equal to 1, so that implies a must be sine of the integral of tau to tau, okay? And plus the angle depends on the initial value, okay? So let's put theta here. 0, let's say use a, doesn't matter where you, when you start from 0, then you have s, okay, for the simplest. And the vs is going to be sine, cosine, okay? And theta is determined by the initial value because a s 0, for example, right, should be equal to sine theta because b 0 equals. If you start with an arbitrary number, then you put s. Okay, so s, and cosine theta, okay? Theta can be uniquely given like this. Great. All right. Wow, great. That's just from ODE. Now you can solve it. So we get very nice, and also AS is not arbitrary. On the other hand, AS must be equal to negative 1 over KX. Wow. So tau and the K are related, right? From these three equations, tau and the K are related. Tau and the K are not independent. So for a curve on the sphere, tau and the K cannot be arbitrary. If you take an arbitrary function, tau and the K, then you're not going to get a sphere curve. Okay? If they're on a sphere, tau and the K are related. Actually, K is determined by tau. Okay? Why? Look at this, right? This implies 1 over Ks equals negative sine yeah, I maybe I should write it this way. Yeah, traditionally we use it should be sine first, cosine first. Let me modify it, okay? I want to change it to sine cosine, a cosine sine. So if this is a cosine, then if this is a cosine, then this must be a negative sign. Let's get back because the solution. If yeah, okay, let's use sine. Let's get sine. Let's cosine. Okay, sine, cosine. Okay, so now you have you have this identity, right? So that this relation between K and tau, right? It's really between K and tau. So with given tau, then K is almost dead. You cannot choose another two. Otherwise, it's not going to be a curve on the sphere. In general, in the space, right? And given arbitrary function K and tau, K is not going to zero. There's a unique curve in the given direction almost, right? Now, but that curve is not guaranteed to be on sphere, but if it's on a sphere, K and tau not arbitrary. K depends on tau by this identity. So that's what we get. Okay, this is for the sphere. Now what do we assume? Okay, let's because we're focused on derivative properties. Assume that C is a closed curve sphere. Okay, if it's closed curve, then so we assume that this is a parameterized from it's a parameter by periodic function, right? So it's from negative infinity to positive infinity to r, okay? Such that gamma 0 equals gamma s and the s plus t. Okay, t is the period. Okay, t is the period. Okay. Of course, we see as the length is always equal 1. Okay. So that means that it's also going to be the length of c. Okay. This implies what? This implies well, that's enough. So if we go back to a formula for gamma, right? So this implies gamma is yeah, that so we must have the following property: Ts equals Ts plus tau, and Ns is going to be Ns plus tau by the periodic, right? It's a periodic function, so Bs is going to be Bs plus tau. Okay. Now using this, then we get the following property. You know, remember gamma is going to be As Ns, right? Plus Bs, right? So therefore, so the coefficients As, Bs are also periodic function. So this implies As equals As plus tau. Bs equals Bs plus t. Right? Right, so everything is periodic. All right, so go back to the equation. Go back to this identity, right? So we have this, we already solved that. So that means sine right? How let's say UPT here, right? Theta is going to be sine so in particular, this is for true for general S. So you let S to be negative S0 people. Okay, so you will get sine theta on the left hand side, right? Equals sine from 0 to tau, right? Okay. So this identity show you that similarly, right? Similarly, this is both, right? Similarly, cosine theta equals cosine so that implies what? That implies the integral of tau must be 2 pi k, right? Yes or no? By periodic function, right? The total torsion is also a multiple of k. Right, so this torsion is going to be, yeah, that's surprise. But we don't have any result about curvature for this portion. We find out the integral of that portion is going to be 2 pi k. The question is whether k is going to be 0 or not. Okay. So if you get a curve on the sphere, you take the torsion, the total torsion, we call total torsion, must be at 2 pi k. Now it's possible it's 0, right? But it's not clear from here, right? We cannot guarantee that is going to be 0. And this is one of the agreeable results for the curvature. The curve can be deformed, but the total curvature, total torsion will be the same number. Right? Now, if it's what happens if it's square circle? If it's square circle, it's closed, right? The torsion is 0, so k is 0. Then if we deform the gray circle a little bit, I think the torsion is still 0. Okay, so think about this, right? So think about this here. Let me draw the closed curve. So this is the gray circle, C, right? So the torsion is 0 because since tau is 0, right? And then you deform a little bit, curves like that. I think it's still torsion is going to be 0. Total torsion. The reason is that can continuously deform to C. Okay, C prime. If they are, if just disturb C a little bit, then the torsion, total torsion continuously depends on the deformation. But on the other hand, it must be integer times 2 pi. So the integer is continuous function. The integer must be a constant. Okay. So you have so this is for C, right? That's for C prime. We can use this notation much better. So it's also 0 in general, as long as C is C is just a slight deformation. C prime is slight deformation of C. Okay, so that's about closed curve on the sphere. Now I'm going to talk about a simple closed curve on the plane. Yeah, a curve is called a simple. A closed curve is called simple if it does not have a self-intersection. And this is the material section 3.1. Okay. A closed curve in R2 is said to be simple if it does not have, if it has no self-intersection. Okay. So curve like that is simple in mathematics. A curve like that is not simple. Right? Because it has a self-intersection in dimension 2, right? And how about this? Let me draw a complicated one, okay? Okay, let me continue. It's a simple curve. Okay, it's a simple curve. The answer is it is simple curve. It is simple. Yeah. Because there's no self-intersection. It is simple. It's still simple, right? And for a simple curve, actually, if you take the total curvature, sine curvature, that's going to be 0. I will explain to you. Yeah, if it's simple, you can always kind of, topologically, you can deform it. You can push this back, right? And eventually you can make it like a circle, right? Yeah, without touch anything, okay? On the plane, this is just like some kind of a string, right? And then you can make it. If you do not enlarge, if you do not, if you keep the same length, then you probably get a very large circle without touching two pieces of the curves. Okay, right? This is how simple. You can change it to quite slowly to a circle. Roughly speaking, yeah, a simple curve a simple closed curve is a closed curve which can be smoothly deformed to a circle without touch each other, touch it, okay, without to touch, just any two portions of the curve will be never touch it, okay. So this is a topological definition of simple curve. And there is a very important theorem. The theorem says that, what's the name of the theorem? The theorem says that it's given by, it's called the Jordan curve theorem. Okay. Jordan curve theorem says that a simple closed curve in a plane divides the plane into two regions. One is called the interior region, the other one is called the exterior region. So a simple closed curve simple closed curve. Right? There are two, always divide R2 into two connector regions, two separate connector regions. Right? One is called the interior and the exterior. Right? Well, if it's a circle, right, then you have clearly the circle is divided whole region into two parts. One is called the interior, right? Other one called the exterior. Okay, it's obvious, right? And here exterior, right? But it's not always obvious in some cases. Just like the example I showed you, and let's draw it again. Right, I'm going to draw this, right? So then I don't touch any side. I can see, right? Okay. So this is a simple closed curve. But does it divide the whole region into two? Does it divide R3 into two connected regions? It's not that obvious, right? Yeah. This is a simple closed curve. Now, which part is the exterior? I think this part should be exterior, no problem. Then you have to determine the interior. I think this interior can be used color. Let's paint it. Okay, you can see that now it's easy to see. It's interior, interior, interior. Right? Yeah, finally. Good. So this is the interior region. Right? You cannot, once you stay inside, it cannot go out in the plane. If you are here, there's no way to go out unless you get across the line, across the curve. Right? Any point inside there, it cannot go out unless you go across the curve. Okay? That's called the interior region. Exterior, yeah, interior region. Okay, and the exterior. Okay. But it's harder to check whether this is a right. It's harder to check. Right. It's not easy. If when the picture is very clear, you can draw a very complicated picture on the wall, and it does look like a simple closed curve. Right. So the yellow region is the exterior. All right. Right. And you can eventually change this simple curve into a circle, okay, without touching any sides, two sides line. So you can deform it, just open this, right? Go this direction and open it. So finally you get one string long, right? Right? Then you continue to deform it, right? Then you continue to deform it, and then you will get a circle, right? Topologically, there's no difference, right? It can do this smoothly. So topologically, those two are the same. You don't see the difference, but geometrically they look different, quite different. One can smoothly deform from a closed curve, for a simple closed curve to a circle. Right? A simple closed curve can be smoothly deformed to a circle, right? Without touching each other, okay? Without touching, right? Yeah, without the intersection. During this procedure, right? All right, now, but there's some curves you can also do that without Yeah, I think even yeah in some let's see, yeah, without intersection. Okay, so that's it. So now I'm going to explain to you the Hopf theorem. Right? Right? We have the theorem called by Hopf for any simple closed curve. Uh, gamma. Right? So the integral of gamma of the sine curvature ds is always equal to plus minus 2 pi. It depends on the orientation. If it goes that direction, it's positive. The integral of ks ds, I think it's positive 2 pi. If it goes in that direction, then the total curvature is negative 2 pi. Okay. Okay, why this is true? Why this is true? All you have to do is just look at the case when it's a unit circle or the circle with radius r. Right? Let's take a look at example. Right? Consider the circle with a radius r. Okay? And then it depends on our parameterization. It's a sine curvature. It depends on parameterization. How do you find the sine curvature? Do you still remember? Okay. let's parameterize gamma s equals r cosine sr. Sine sr. Right? In this case, we already did a calculation. Right? The sine the curvature is always equal to 1 over r. We already did this before. Okay, this s is arc length. Okay, it's the derivative of gamma as a unit length. Okay. So let's find the total curvature. It's integral from 0 to 2 pi r because it's a whole circle from circle from 2 pi r. Okay. And ks ds. Ks 1 over and ds. So it's r times 2 pi r cancelled out. It's equal to pi. So the circle is oriented in this direction. Yeah. So the closed curve, simple closed curve, can be deformed smoothly to a circle with radius r. So therefore, because the total curvature, total sine curvature is 2 pi k. K is constant. K smoothly depends on the parameters of the formation. But it's smooth, right? So if it's also constant, then you cannot jump in. So that's why it remains to be the same constant, given this definition. Right? So that's why that is why for any simple closed curve, the total sine curvature should equal either 2 pi or negative 2 pi. The sign depends on the inner orientation. Right. Now let's continue to study this curve. Right. Uh, there's a famous theorem in section 3.2. It's called Green's theorem. Yeah, before we do that, let's study the closed curve, and we're trying to figure out the area of that region, right? So this is a gamma. Right? So the area, right, of the region, right, interior region, right, increased by gamma is denoted by a gamma, okay? Yeah. And this is the interior air, right? The interior region, right? So a gamma, when you calculate, right? How do you how do you find this double integral of the interior of a region and dx dy? Yeah, that's the area formula. That's by definition, right? Now, the green sim says that uh, you have this double integral, the interior of the gamma, and partial derivative of with respect to x, right? That's dx dy is just equal to the line integral along the gamma. F is the x plus g dy. Right? Now this is it's a line integral on the right hand side. This is a very useful formula because in order to get the area, I just take let g xy to be x, f of xy to be y. Okay. Then the partial derivative to be negative y, for example. Yeah. Then the partial derivative of f with respect to y, get a negative one, then negative becomes positive. So what you get here is 2 dx dy. And this is gamma, f is negative y dx plus g is x dy. Right. So finally, we have the area formula. Okay. And this is a useful formula to calculate area. And you change the double integral into a line integral, right? Yeah. So let me give you the problem. Okay, find the area of the ellipse. Described by this equation. Right, can you try this? How do you solve it? Right. So think about this. Okay. Let's go back. Work on this problem. So using the above formula, we can easily find the area. Otherwise, it's very difficult, Use the double integral. How do you use double integral? You have the double integral on the ellipse, right? So this is a gamma, okay? And yeah, in the green theorem, the orientation is important. This is a gamma, okay? It should be oriented in that way, okay? Counterclockwise. Okay. So here, let's choose x to be a cosine t, y to be b sine t. Right? This is the parametrization for the curve. So the area of the ellipse is going to be half of the integral, right? And this is a gamma. So gamma is parameterized by this, right? Gamma is given by this. Yeah, gamma t is going to be a cosine t, b sine t. So here should be from 0 to 2 pi. And let's see, what is negative y? Negative y is negative b sine t. And then dx is going to be negative a sine t dt, right? And then plus x a, oops, where's my y? So it's going to be plus, hold on, I think my pen has no barrier. Just 1 second, okay? So you plug them into this integral. Whenever you see dx, it will become negative a sine t dt. And then add them together, you will just get a b here. Yeah. So cosine a t and the d then dy, so d cosine t. Yeah, I need a wait couple seconds. So after you enter all the the function, then you will get the integral of just the ab. Right? So that'll be negative b cosine t dt. So here 0 from 2 pi and inside is ab dt. So that's why ab. Okay. So the area of the ellipse is just the product of a and b. That's good. That's great. That's interesting. Okay. If we just want to use evaluate triple integral, double integral over the ellipse, it's a difficult. Okay. It's not easy to evaluate the double integral. And that's multiple calculus problem, right? So ellipse is just a deformation of the circle, not any other region. We cannot find the area easily, right? Let's try Yeah, think about any closed curve. No, I don't have any good one right now. Right. Okay. So that's this is about area formula, area of the ellipse. Well, let's take a look at the. Can we figure out the arc length? The arc length. We don't call circumference, right? The parameter. The parameter of this ellipse. Okay. It's going to be called L gamma. Okay. This, by the definition, is going to be integral by the formula, right? It's integral from 0 to 2 pi, the length of our parameter, right? Right. So let's try and find it. This is going to be the derivative. It's negative a sine t squared plus b cosine t squared and dt. Unfortunately, this is cannot be simplified. Right? This cannot be simplified. Now but is there any estimate you can do? And on one hand, we have a gamma equals AB, right? And then we have the above identity. Okay. So if the area fixed, okay, can we? If the region, right? So this is a fixed area, okay. This is the area, right? And we want to look at the comparison. Yeah, we want to look at a comparison. So first of all, let's look at this sphere, right? Let's consider. I'm going to. Yeah, I'm going to consider the following ratio. Doesn't matter which one's on the top, okay? Gamma, yes. I'm going to put the length on the top. Okay. This ratio, yeah, what is the possibility for this ratio? This is well, if you don't, you can also consider like it's a square of the area divided by the length, and then you square it. So, okay. So in other words, you are going to consider this rate, the square of AB. Right. So can we make this number as small as possible? The answer is No. But can we make this number as large as possible? The answer is yes. Okay, why? Because you can make this region getting longer. Right? And you will see that the length is getting longer, but the area is probably getting smaller. Fix the area. So in general, there's no upper bound. But can we do this estimate? Can we estimate this ellipse, right? Ellipse. Yeah, does it have an upper bound, lower bound? Can you estimate? My claim is the lower bound, the smallest possible value of the risk ratio is going to be 4 pi. And what happens when A equals R? Let's take it. And this is true when A equals B, okay, equals radius, when it's a circle. So this is just a calculus problem, right? Okay. Yeah, let's look at the case when look at the case when A equals B equals R. Let's look at this ratio. This integral from 0 to 2 pi A square, this is sine, right? This is sine square T, B square cosine square T dt over square AD, right? That is going to be, I think the area I'm missing something here. Okay. I think this is a pi is missing, so this should be pi. But otherwise, something will be wrong. And it's still pi. And this is still pi. Yeah. All right, so let's take a look at in this case, A equals B equals R. So it's going to be integral, and here's R. And then this is just R, right? And here's a dt. And then here, this will be A times B, that's R squared. So just equal to R again. Okay. So the answer here will be R cancelled out. It's a 2 square pi. But when you square, it's just 4 pi. Okay. So right. Now in general, it's not easy to prove, right? I just want to say, this is when it's a circle, the smallest possible value is reached by the circle. Okay. So in general, okay, we always have this encoded. Okay, this is what we're going to do the next time. Okay, this is called the isoparammetric encoding. right? The isomorphic inequality says that for any simple closed curve in R2, right? Right? The length of gamma, right, divided by the square root of the area, right? That's a square. It's always greater than or equal to 4 pi. Or you can simply write like this. Now, what does that tell you? Then I'm talking about application first. That tells you, then equality holds if and only if gamma is a circle. Only the circle. Only when the circle is true. Okay. Yeah, in the circle case, this is a pi r square. This is a 2 pi r square, right? After you simplify, you get 4 pi square r square pi r square. After you simplify, this 4 pi. Good. That's a square. Right. So that inequality can be also written in gamma less than or equal to 1 over 4 pi of the square. So you can conclude that among conclusion. Oops. Okay. So among all simple closed curve with a fixed parameter, right? The circle has the largest area. Now, this probably human being already knows this, but it's never get a proof. Right? Never, you have to prove that in mathematics. Okay, so if you're given a piece of a fence, for example, right? And this is 100 feet. You want to include the region with the largest possible area, right? So how do you do that? You have lots of choices, rectangle, right? And you can have a square, right? You can have a triangle, but circle has the largest area. Okay, so that's why people pretend to make a circle. For example, like Mongolian people, right? They live on hot, right? They load their tents, right? Okay, when they stop somewhere, they want to make a house, a tent. So of course, they want to make the area as large as possible. That's not the installation is still simple. Then because they can include more area, make a circle. A circular tent, right? Circular tent with the same material gives you larger area, maybe not comfortable, right? And this is the most economic way. Okay, so now we prove that among all the closed curves, simple closed curves with a fixed parameter. Okay, we can smooth it a little bit because those are not a smooth curve, but it's okay, just tiny bit. Right, it looks like almost square. Okay, and circle has the largest area. The reason is if all of them has a fixed parameter, right? According to the above formula, it's going to be p squared over 4 pi. Okay, area never be larger than that. The square of the parameter divided by 4 pi. Okay. Now, and the equality holds. If we want to get the area, which is going to be pi squared divided by 4, if and only if gamma is a circle. Okay. And simple closed curves can be very complicated, right? It's not necessarily like a rectangles, square, triangles. For high school students, maybe they can prove that for the same parameter, rectangle and the triangles, their areas with the same parameter, the area will be smaller than the area of the circle. Okay. But here we are talking about very general closed curve, simple closed curve. Okay, it could be anything like that. Okay, this is a simple closed curve, but it includes a much less area than the circle. As you open it, the circle is a very large circle because the perimeter is pretty long here, pretty large here. Okay. Right. In the book, they give a proof, right, without using complex analysis. And if we use a Fourier expansion of a periodic function, the proof can be much simpler to show that the area is going to be less than or equal to the square of the parameter given by 4 pi. Okay? You can always assume that the parameter is 2 pi, make it simple. Okay? Because by scaling, no problem. By scaling, no problem. All you have to do is when p equals 2 pi, you want to prove that the area is going to be pi. Okay? Yeah, we may assume that the p is 2 pi, and we want to prove that among all the closed curves, the area is going to be less than equal to pi. Okay. The proof using, if we have to find another proof, the proof will be using expansion of not Taylor expansion, Fourier expansion of a periodic function. But in this book, they use a very basic inequalities from calculus, linkages inequalities to build it. Okay. Well, we try to prove that next time. I'm not going to have enough time to do this. And those are the about the Gruber properties of a closed curve. And at the very beginning, I was talking about closed curves on the sphere. Maybe further study maybe to be done for curves on the sphere.